to meet Francesco Evangelista from Emory University in US, and he will speak about projective quantum algorithm for quantum chemistry. So thank you for listening to you.
Good morning, everyone. Thank you for the introduction, and I would like to thank the organizers for putting together this very nice workshop. So I am a quantum chemist, and I'm going to talk today about some of the projects we've been doing in quantum computing. So I want to start by with acknowledging the people that have worked on this project. So I'm going to mention work done by Nick Stair, who's now working at PC Ware. He was a graduate student in my group. Jonathan Mizovic, Elias Magoulas, and Ranka Wong. This work is done in a broader collaboration that we have, and it's funded by the Department of Energy. This is called Quantum Chemistry for Quantum Computing Research Collaboration. And these are some of the code beyond involved. So, why I want to tell you kind of what is the grand plan and how do I envision as a chemist incorporating quantum computing in my research. And the idea is to basically decouples degrees of freedom. And we want to treat weak correlation, things that are easy with classical methods, and the hard part with quantum computing approaches. So suppose you have a system with many orbitals, many levels. We want to be able to partition this into, a couple to hundreds of orbitals. These might be near degenerate and give rise to static correlation, and separate these from the rest, which might be either double occupied or weakly unoccupied. And these are mostly responsible for dynamical correlation. But as a quantum chemist, I know that maintaining a good balance between the description of these two parts is actually essential to getting high accuracy. So here's an example where you could use a scheme like this. Suppose you want to study a reaction on the surface. We have a small molecule interacting with a semiconductor, and say we excite this molecule vibrationally. I'm referring actually to an experiment that was done that looked at this molecule on sodium chloride. Here we have different degrees of freedom. We have the orbital degeneracy that builds up as we stretch the CO molecule. We have the molecule surface interaction and the surface itself that we have to represent. So a scheme like this makes sense in a context like this. So what I'm going to cover in today's talk, I want to talk about two aspects of this research. First one is new quantum algorithms that we've developed to deal with strong correlation, or towards strong correlation. So I'm going to introduce you to the projective quantum eigensolver, and then I'm going to discuss this new paper, which is not yet gone through the full peer review process, that is about how to scale small quantum computers using unitarily unfolded autonomy. And these are going to address the two aspects that I mentioned above. Okay, let's start with the quantum algorithms. So I guess when I started studying quantum computing, I had this kind of like developing view of things. I heard about phase estimation, I'll talk about all these algorithms in the context of kind of like Minecraft-like map. So you have phase estimation. This is king among all the quantum algorithms. We know how to handle circuit compilation. There's the problem of characterization. It seems to be dealt with. But you have these mounds of decovariance that prevent you from really doing much these days. But that view has been expanded afterwards with the introduction of the original quantum algorithms like PQE, which suffers from the Baron-Platel issue, and has this feature where we seem to be able to come up with thousands of different ansatz that you could use with AQE. And I think for a while I thought, my view was like, here there are dragons, and so don't go beyond the water. And what was interesting, so the first thing to avoid is the sea of bad ideas, which we can all swim in at some point. But to me, what was interesting was these methods based on subspace, quantum subspace methods, like Q-launches and imaginary time propagation methods. Those are very interesting. I know there's been some talk about quantum parallel methods, but today we're going to visit this other island of projective algorithms, which I would say has a strong connection to quantum chemistry, and it's complementary to all of these other groups. We also have to remember that there might be many more unexplored quantum algorithms. And so I find this field interesting because of this unknown territories that are out there. Now, I mentioned phase estimation is king among all the quantum algorithms, but sadly, the reality today is that we can't run it on these devices. So recently I did this IBM quantum challenge, and I played with the seeding model with 5 sites. When you factorize the dynamics, you get a very small circuit like that. And when you run this on a simulator, you say flip a spin, propagate over time, you can see this kind of spin propagating, bouncing back. But when you do this on a device, you get something like this. And I'm not showing this data to necessarily point out, to discuss the quality of the IBM machines, just the general status of the field. With this kind of noise entering in, it's difficult to do things like phase estimation. If we want to work practically with these devices, we need to use something that is tailored for these devices, like variational quantum eigensolver. And this has been mentioned quite a lot by now. We're all familiar. It's basically a energy minimization problem. You have a trial state. They generate through some unitary. Through quantum measurement, you can measure the energy or the gradients with respect to these parameters T, and then do a classical update and iterate. Now, as I was looking at theory, in my group, we had some questions. Some of this were, could we realize trial state optimization without this form of energy minimization? At the time we asked this question, it wasn't obvious how to compute gradients efficiently, but now there's been some work in this direction. And it's interesting, what I'm going to talk to you has parallels a little bit the work of Schroeder and coworkers that proposed an efficient way to compute gradients. And I would say state-of-the-art PQE algorithms do not rely on a fixed trial state, but they adaptively produce a trial state that is optimal for a given target quantum state. So can we do this selection in a different way? So nowadays, people compute the gradients along all the parameters and identify which operators to have. So we're going to try to address these questions. So we came up with this idea we call the projective quantum eigensolver. Now, from a quantum chemistry perspective, this is pretty trivial because it's almost a translation of coupled cluster theory. So we were surprised that this was not kind of proposed before in the literature. The idea is very simple. So we again start from some trial state parameterization. Right now, we're just concerned with finding the optimal parameters T. We'll have to see in what sense we mean optimal. But instead of going through the expectation value, what we do is we plug this in the Schrodinger equation, left project by U dagger, and we end up with this equation. Here we have a similarity of unitarily transformed Hamiltonian. And then what do we do? Well, to evaluate the energy, we project onto this state, this uncorrelated state, and we get an expectation value expression. This quantity is variational, and it's the same way you would evaluate the energy in BQE. The difference is that instead of enforcing the gradient equals 0 condition, we do something slightly different. We project this equation onto complementary states to this reference, and this gives us a set of residual equations. So these residuals are quantities that are different than gradients. They're related to gradients, and maybe I'll mention that at some point. These set of conditions are we call projective conditions, and are what you would use in coupled cluster theory. Okay, so what are the challenges with dealing with this kind of scheme? First of all, let me give you a few more details. I'm interested in fermions, so I want to tell you a little bit what are these states and these operators that I'm concerned with. So the reference state is a Hartree-Fock determinant, so it's going to have some occupied holes, particle levels that are empty. And when it comes to the unitary, we use the coupled cluster parameterization. Now, just to distinguish this from the traditional unitary parameterization, we call this factorized, disentangled ansatz. And so you have a product of exponentials where these operators kappa that enter these exponentials are particle hole excitation, the excitation pairs. So these kappas are anti-emission, which makes each of these unitary. Now, what's interesting about this scheme is that if you do, say, a quasi-Newton update, you get a very simple type of equation update that's different from what you would use if you had the gradients. So you get these residuals. In principle, you evaluate them, divide them by some molar plus denominators, and you get a simple update equation. And we then can use techniques that have been well developed to accelerate the convergence of these equations, like Pouillet's DIS method, which is an iterative subspace accelerator. So now I want to mention just another work that we did. This would be interesting to discuss, but I don't have time. Is that, so why do we choose this ansatz? Okay, and is this kind of an empirical choice that we made? Well, in a paper that we wrote in 2019, we showed that this form of unitary coupled cluster theory can actually be exact. But there's a caveat, and it depends on the ordering of these operators. These kappas here don't necessarily commute, and so different orderings give you different ansatz. And these different ansatz have different potential to cover the entire Hilbert space. But there's certain orderings that can represent any quantum state starting from a given Hartree-Fock reference. So that guarantees that we can converge to full CI, in other words. So what is the thing that maybe the aspect that was that prevented or that seemed like a roadblock in a method like this is the evaluation of that residual that I mentioned before. So I'm going to show you a very simple scheme that Nick came up with to evaluate these residuals. So to look at the schemes, I have to introduce a kind of rotated reference state. So this is a state that starts from the Hartree-Fock reference, and we apply only one of these excitation operators, kappa mu. So for each excitation operator, we can define one of these states. And we'll make that state dependent on the angle theta that makes it. And I'll consider this excitation value of the energy for the similarity installment with respect to this rotated state. So why is this useful? Turns out that you can express the residual exactly as the difference of these excitation values computed for pi over 4 and minus pi over 4. Now, if you look in the original paper with Nick, we actually report an expression with 3 terms, but then we realized, well, we just need 2 terms. So the evaluation of one element of this residual requires the evaluation of 2 energies computed with respect to a reference that has been shifted in 2 different ways. Now, if you compare to the shift rule used to calculate gradients, they look very similar, but there's an important difference. So we put the shifts at the beginning, well, I guess at the beginning of a quantum circuit. Well, these when you evaluate gradients, the shift happens in the middle of your ansatz. So pretty simple, pretty straightforward to do. We have to pay the price of 2 energy evaluations. Right, so let's take a look. It's worth doing this technique. So what we found out, so this is I would view it as a different way to realize VQE using a different strategy. What we found out when we apply it to small molecules, say, for example, linear chains of hydrogens, is that we see faster convergence with respect to VQE. Now, this comparison is tricky because you're using very different techniques to optimize the parameters. So here we use this Polari acceleration for the projective quantum accelerator, and we use analytic gradients for VQE and LBFGS. So we use pretty kind of heavy technology to accelerate these calculations. And what we can see is that VQE tends to be slower, and you have kind of a size effect. So the bigger the system, the higher the number of iterations. While with this projective method, at least in this case, we did not see a strong difference. Another aspect we investigated was the resilience to noise. And here we did a very simple form of modeling noise. We just added Gaussian noise to these residuals or to the gradients in VQE. And what we looked at is how a calculation converges as a function of the noise level. So here you have the standard deviation of the noise, say 10 to the -3, and you have the performance of PQE and VQE. And we see that both are still resilient to noise, and we keep this faster convergence for PQE. This is done sampling several calculations on this H4 molecule. So at some point I mentioned that really state-of-the-art in VQE requires some form of adaptive build-up of the enzymes. So I want to tell you how we extended this approach to do that. So a natural way to so in techniques like adaptive VQE or qubit couple cluster, you use the gradient of the energy to tell you which operator to add. Here we are starting by saying we don't want to evaluate gradients. So what quantities do we have an handle on? We have these residuals. So a simple idea is to say, well, let's evaluate all the residuals. If we find a residual that is large compared to others, we'll say that the corresponding operator is more important. And so we might want to put that into the ansatz. Now, how can you justify this idea? So we use the Verschoren circle theorem that basically says the following. If you take a look at that similarity transform Hamiltonian and its matrix representation, we can put a bound on the difference between the exact eigenvalue, the exact logistic eigenvalue, and the element that is there. And that difference is less or equal than the sum of the absolute value of the residuals. So this justifies the idea that as we pick the largest residual and we introduce an operator to eliminate that residual, will improve the quality of our answer. Now, in principle, in our technique, we have to sample operators of all ranks. So singles, doubles, triples, quadruples, and so on and so on. And this is something that could become easily the major issue in an algorithm like this. In these other algorithms that I mentioned, with couple cluster and AppVQE, you would select a pool of operators. For example, in AppVQE, you would select generalized single and generalized double excitations. So the reason you restrict this pool is because you have to do less sampling and yeah, you speed up the method. However, it was unclear to us whether it's better to use these operators, which potentially can express better certain operations, versus these singles and doubles only. So let's look at how we solve this idea of sampling all these residuals. So we thought about using quantum measurement as a resource to accelerate selection. So let me explain the idea that we had. So in principle, we need to evaluate all the elements of this residual vector, which has size full CF. So what we decided to do is to try to create a state on the quantum computer that is proportional to this residual vector that we need to evaluate. Now, the state, the actual residual is not a normal vector, so we can't generate it directly. And we therefore opt to approximate it in this way. We similarity transform the time evolution of the Hamiltonian. Because under short times, you can see that the leading term here is the reference plus the residual itself, the quantity we want to evaluate. So what we do in practice is we generate the state for a small time step t, then measure it. And that gives us a bit string. That bit string corresponds to one of these excited determinants, and therefore one of the operators. This determinant will come out, will be measured with a probability proportional to delta t squared and the residual squared. So in practice, we sample this wave function, and by the process of sampling will tell us the determinants that are needed to improve the ansatz. And then the way we use this information is the following. We kind of make an histogram. We select a few, and the number of states, the number of new operators we add is determined by kind of a bound on what we throw away. So we decide how much we throw away, which is this omega parameter, and therefore what's left is what we introduce. So we introduce the operators corresponding to the largest residual and control how much we throw away. So this is the parameter that controls the accuracy of these calculations. So let's take a look at how this selection works. So if you use a small value of this selection criterion, you will get very compact ansatz, but these they might not be super accurate. So here's an example where I looked at beryllium hydride as a function of the beryllium hydrogen distance. And you can see the comparison with respect to unitary couple cluster singles and doubles and Hartree form. Here we have H6, and again, energy error with respect to CI as a function of the quantum distance. So here we produce ansatz that are compact, but are not necessarily more accurate. Now we have that parameter, we can make it smaller, we can decrease it, and we get very accurate wave functions. And our parameters have to adjust. And in both cases, you see what you would expect. You see a buildup of multi-determinantal character, and therefore the wave function becomes larger. We use more parameters, and we maintain good accuracy. The comparison with adaptive QE is possible, but these are two different selection criteria. But you can find values of their criteria that basically reproduce the numbers that we generated. You see some interesting features with adaptive QE, but I don't want to linger too much on that. What I want to show you, though, is one thing that we at least experience numerically, is that when we use adaptive QE, so we have our own implementation, we also have access to the original implementation, we see that the number of these gradient evaluations that we have to do in adaptive QE is significantly larger than the ones we do in SP3, the selective version of the projector quantum accelerator. And this cost comes from some algorithmic choices, because you have to compute all these gradients, and then in their approach, you pick one element at a time. So there's inefficiency built in. Now, one thing I want to show you though is this. It's easy to compare to Hartree-Fock or CCST, but when you go to compare with standard quantum chemistry, you really get into a very tough race. So as part of his PhD, Nick also worked on these hydrogen systems where we look at chain 10 hydrogens in one dimension, a triangle lattice in two dimensions, and a little pyramid So we studied these because we wanted to look at how electron correlation changes as the dimensionality of the problem changes. We compared to techniques like DMRG, selected CI. So it's a variant of SIPC developed by Jean-Paul Mariot. And here what I'm plotting is the energy error as a function of the number of parameters in these ansatz that I've compared. So these are classical. This is the unitary couple cluster based selected PQE approach. And you can see in one dimension, DMRG kind of outperforms everything. Here we use a localized basis set, which is very important to get this kind of performance in DMRG. And you can see that this quantum trial state optimization with these kind of selected ansatz kind of do better than linear ansatz that we use traditionally in quantum chemistry, but they still can't outperform DMRG. Now in 2 dimensions, things start to become more difficult for DMRG. And that's where we see kind of the advantage of using quantum algorithms. Classical methods like selected CI still struggle a little bit more. And then in 3 dimensions, you see something similar. Now, of course, this is very small. I wouldn't say, don't generalize from this little data to bigger clusters or infinite models. So, but it's interesting to see that quantum algorithms have to still advance to outperform DMRG. Now I kind of want to quickly transition to the next topic, and but before I do that, I want to tell you a little bit what we're doing, what the work that is unpublished that followed from this project. So one of the things that we noticed is, so we like the selected approach, and we want to continue to develop it, and eventually actually run it on hardware. But one thing that we noticed is that as we say, take a molecule like this H6 model and stretch it and build up correlation, we look at our circuit lengths and they increase drastically. Now you expect this to happen because you added more operators, but this rise is quite a little bit too high for what we would like. So when we analyze what happens is the issue can be traced back to the kind of trickling in of triple and higher level operators. So when we want to describe the static correlation, we have to add triples or quadruples in our ansatz. And now I haven't talked about circuits, so I want to kind of go to discuss how the actual circuits that we implement look like. So we have these quantum circuits that are becoming larger and lots of CNOTs. What can we do to reduce the cost of implementing these? So one strategy that has been proposed, and Arthur was here yesterday, so he didn't talk about this former work, but it's the idea of using a basis of qubit operators. And simply, this consists of taking fermionic operators, doing the Jordan-Wigner transformation. So we convert operators to a Pauli basis, and then ignoring these Jordan-Wigner strings that encode the fermionic sign. These operators that are left, Q, they satisfy the algebra of pair fermions, so you can't put 2 pair fermions in one level, but they commute like bosons. Now, what we've found in the literature is some work done by Yordanov, where they propose very compact circuits for these exponentials of qubit operators. Yordanov studied the case of 1 in single and double qubit excitations, and we liked a lot their circuit cost, so we decided to extend this to arbitrary order. So Ilias Magoulas, who's a postdoc in my group, extended this construction to an arbitrary order qubit operator. And the way you do this is it's not through the traditional route where you Jordan-Wigner transform everything, and then evaluate the exponential. If you do it that way, you get what are called staircases of CNOTs. The approach is different. It's basically, and this is an idea by Jordan, you basically write down a circuit that transforms the states with the correct. So for example, in this case, we have a series of operators that annihilate these peripheral elements. And create some other peripheral elements. So you basically just create this operator that rotates these states with occupied perifermions in these orbitals, and have these corresponding other perifermions orbitals empty. So and the way you do that is by this cascade of CNOTs that basically make sure that certain qubits are unoccupied and some qubits are occupied. And then you have this multi-controlled rotation gate. So now if you decompose this gate, you can break it down into CNOTs, but the count is much smaller. In fact, when we compare the standard CNOT count for the kind of conventional way of converting exponentials, we kind of we still are exponential, but we lose some prefactors. And that practically has kind of a drastic effect, because we can achieve CNOT reductions on triple excitations, quadruple excitations of orders of 87, 92. And this gain is high, it becomes bigger as you go to higher operator rank. So here's some data. I want to show you, first of all, what happens when we can do this also for fermionic operators. And what happens, of course, the energy is exactly the same. The size of the ansatz that we get, the number of residual evaluations that we do are the same. What changes here is just the number of CNOTs. So if we say take a fixed ansatz with up to quadruple excitations, this requires 155,000 CNOTs. We can reduce that by a factor of 10 to 15, roughly. And we see a drastic reduction also in the selected ansatz, where we can reduce the number of CNOTs significantly. And this is just the way we encode the ansatz. Okay, this doesn't have to. We're not counting measurements of the Hamiltonian elements. Okay. So this is a very neat technique, because it's just it's a gain. Don't lose anything. Another thing that we looked at is, what if we throw away these Jordan-Wigner strings, and that in principle can achieve even more drastic reduction of the number of CNOT gates. But then you change the ansatz, so you'll get different answers. And what's interesting is that we see that now these methods with fixed ansatz, say like the triples, they lose accuracy. So you go from an error of a couple of milliarchy, which is nearly tolerable, to something that is much larger. We use the same ansatz here, so the number of parameters is the same. We save just a little bit in terms of CNOTs, and we also have to do more iterations to converge the equations. So this is something that I think other people have noticed too when you switch to this qubit basis. And this doesn't end up helping too much in the selective approaches. So, so now we are a big fan still of fermionic operators. Well, initially we thought that these qubit operators were led us to an advantage, which apparently for our method is not obvious. Right. So let's see. Should have a okay. So now I want to switch gears and talk to you about, like, suppose now we can do these calculations. What can we do? How we couple those to classical Hamiltonian Dunn-Fulton. So this is actually a topic that is really dear to me. I've done my PhD in something called multi-reference coupled cluster theory. So always dealt with these issues. So what are the main issues in coming up with a good, effective Hamiltonian theory or Dunn-Fulton technique? Quantum chemists would refer to these as multi-reference theories. And the idea is to, again, produce an effective Hamiltonian on a limited number of degrees of freedom that represents the physics of low-lying electronic states. So first of all, when you build a model, you need to have an idea of what state you want to represent, because building a model is a little bit like doing a Taylor expansion. You have to decide a point where you have to expand about. And if you happen to be very close to the solution, the model you produce is going to be very easy to solve, and it's going to be not very complicated. So we need to have an initial state. Where can it come from? Does it come from a quantum computer? Can we generate it classically? Typically, when you do realize a scheme like this, I would say most schemes will require to know some information about this reference state. And that comes in the form of density matrices. So how much of that density matrix really matters to perform this effective unfolding? You need unfolding methods that are noise resilient, because there might be some quantum input into this classical method, and it needs to be accurate. And I think this is something that needs to be appreciated. From quantum chemistry, we know that if you want to do something like this accurately, say at least with many body methods, we need to account for at least two body interactions explicitly, and likely perturbative triple, so three body terms as well. Here's some work, others that have done unfolding. I'm just gonna go quickly over that. So I want to tell you about what we do and where kind of the idea that we use comes from. So we use a technique that we call driven similarity to randomization group, and it looks like this. So it's going to be a transformation of the Hamiltonian done with a exponential of an anti-Hermitian operator. This technique looks very similar to what I presented before, PQE and couple cluster theory. The only difference is that now this transformation depends on a time-like parameter S. And this parameter S is going to be helpful in this context, because what we are going to consider is not just a one-shot transformation, but more of a renormalization group transformation. So this parameter S that is going to enter here and control this transformation is going to be such that it's going to be related to kind of energy cutoff. And when we perform a transformation of this form, we require that the transformation eliminates coupling between states that differ in energy by a difference that is greater than this point. So let me kind of illustrate that graphically. Let's start from a many body operator. Like here, I write the tensor representation of the two body component. When I start in this flow renormalization approach, S equals 0, and I have all the elements of this tensor, and they're different blocks. So there's the core active, there are different parts of this Hamiltonian that are there. And I want to reach a block diagonal form. And why do I want to do that? Because I want to decouple the orbitals that are going to represent my effective Hamiltonian from the rest. So I do that by introducing 0 in certain blocks of this tensor. Now, if I do it with a similarity randomization group approach, what I do is I kind of slide this parameter and slowly eliminate these couplings. Now, why would I do this? Is because by doing it this way, I avoid eliminating the coupling for terms that correspond to very small or 0 denominators. So if you're familiar with the intruder state problem, this is a typical, if you count for the elements that are left here in this transformation, say just through perturbation theory, you would run into this issue where you get 0 denominators or very small denominators, your perturbation theory blows up. So this is a way to avoid that issue and control the transformation. So how do we do that in practice? We do this transformation. We do this in the language of normal ordering with respect to a correlated state. This is techniques that have been developed in the late 90s in quantum chemistry. And once we have the similarity transform Hamiltonian represented as a mini-body operator, what we do is we take the components that, as I said, bring us outside this effective Hamiltonian, like for example, excitations from core to active or core to virtual, and separate them from excitations within the active orbitals. So these configurations here, so these excitations will take a reference state and send it outside the space we want to describe with the effective Hamiltonian. And so we basically want to eliminate them. So the kind of equations we want to solve are equations where these tensor elements are set to 0 and these are left to be what they want to be. Okay. That kind of condition that I mentioned will look like that. And then if we use this, if we build a connection between this transformation and this flow renormalization group approach, we get this idea that we call driven similarity renormalization group, which is a different way of realizing the same kind of similarity transformation. And instead of doing it by solving a differential equation, you do it by solving a nonlinear algebraic equation. So here you have this extra term, which we call the source operator, which has a well-defined form. And by adding this extra little component, we can basically reproduce that renormalization group flow behavior. So these things are not the same things. The advantage of this technique is that now you basically have a set of nonlinear equations that you solve, and you get your effective Hamiltonian. So this operator A that enters into this transformation is decomposed in many body components, like one body to body up to some truncated limit. And these are differences of excitation and de-excitation operators. I'm using here the kind of notation used in couple cluster theory. These operators perform generalized excitation in the sense that they excite to these generalized souls to generalized particles. And now you can see that there's this interesting feature where the definition of my whole and particle overlaps. And this is typical of a multi-reference formalism. Oops, I went back. So how do we adapt this idea to kind of quantum computing scheme? So the idea that we had here, we call this to make the acronym even longer, quantum-driven symmetry randomization group. The idea is to embed this technique into a scheme where you first do, typical orbital optimization. Then you prepare some kind of reference state, which means you diagonalize your Hamiltonian just in a space of active orbitals. Out of this diagonalization, we get a reference state. And what we do here, with respect to the classical approach, is we do a kind of aggressive truncation of the reduced density matrices that enter into the DSRG downfolding. Here, actually, we approximate the cumulants, which are related to the reduced density matrices. They're the reducible part. So once we have these kind of approximate cumulants, we perform a transformation, we get an effective Hamiltonian, and we do an eigenvalue estimation. So here we can do VQE, we can do phase estimation. Now, in the interest of time, I just want to focus on maybe a couple of aspects here. So here's the definition of the cumulants. So the one-body cumulant is just the density, one-body density matrix. The two-body cumulant is the two-body density matrix minus this kind of disconnected term. So we came up with a couple of approximations. The first one just uses the diagonal part of this one-body cumulant. This is a very drastic approximation, but practically it's useful because it means that if you perform this step on a quantum computer, in addition to measuring the energy, you just have to measure the diagonal elements of these cumulants. Kind of more fancy approximation is this 2-QDSRG, where we keep the diagonal elements of the two-body cumulant in the entire one body can move. So we've done benchmarking. And our paper is on the archive. I just want to show you kind of the two main things we can achieve with this kind of technique. So here's a calculation done on H2, but now on a 5Z basis set. And the way we use this technique is to say we have 110 orbitals. Of course, we have only 2 electrons here. What we do with this technique is downfold everything to a 2x2 effective Hamiltonian. This problem we solved with a quantum computer, but because of the symmetries that we have, number, spin, and spatial symmetry, you can reduce that actually to a qubit, to a single qubit. So we come up with a very simple ansatz for this 1 qubit state with just a RY gate, encode the Hamiltonian in terms of polystrings. And we actually run this on a device, on our IBM device, Lagos, and we get very good agreement with full CI done in this 5C basis set. You can see these are experiments, so we have a spread in the results, and these blue dashes here represent the average of a set of experiments. We do, I think, 10 experiments for each geometry. This is I think this is also a very exciting result. Here is a modeling of a chemical reaction done with this technique, where now we can take a molecule like this, which has about 200 orbitals, and we downfold again this problem to a 2x2 Hamiltonian. We can do that because the most important aspects of the chemistry of this problem is this this rotatory transition state, which has dialectical character. And so what we do here is capture with the quantum computer this various degree of dialectical character, while the classical calculation captures all the rest of the dynamic information. This is a difficult problem because you might get this part well, but this part not so well. And here we've done again noiseless simulations and device calculations. There's good agreement with data reported in the literature where people have estimated this barrier here, unrotatory barrier. There's some estimate for the experiments that it's about 40 kilocalories per mole, and even some DMC results that looked at this barrier in high-level couple cluster techniques. And we seem to be in very good agreement with those. Okay, that's going to be the last content slide, and I just want to conclude by this week. We've talked about these two techniques, but we have done several other things. We've developed software, developed other algorithms that I didn't have a chance to talk about, and I touched on some other aspects of our work in quantum computing. With that, I reached the end of my talk, and I look forward to any question.
Well, thank you for this free talk. I think we have for questions.
Talk regarding the exact product ansatz for the QE.
Yes.
Is it also possible to have an exact ansatz but considering truncation of UCC, CTSD, but repeating all the because if it's
yeah, so in our paper, we actually have, in fact, that was actually our original motivation, is when I saw the ADAPT paper, I was like, oh, how do we know that this ansatz built by ADAPT is going to be exact? No, there's more work that I would point you to that Sophia at Barnes and Nick may all have done on that. But from our point of view, the way we can understand the connection is we take that product ansatz that we know is exact, and then we break it down into simpler operators. So we can do that in terms of singles and doubles that are generalized. And you can show that you can write any state with that, but you need, in principle, kind of a, you can approximate it better and better and better. So So I'll speculate. So I have a I would speculate that it's probably true that you can build an exact ansatz full CI number of parameters just using general singles and doubles. So there's numerical evidence for that, but not formal evidence yet. So,
Okay.
so what the answer you could do what you're saying with an infinite ansatz in principle, but I think it's also true for a finite ansatz.
Okay, thank you. Just a related question, you showed some very peculiar behavior at the end. You understand peculiar behavior?
So I think that is, I think you should expect it. And I think maybe you mean things
Yes.
like here, yeah.
Yeah.
What is the criterion used to apply it out? It's a gradient criterion. So you look at the operator with the largest gradient. And once you reach, once all operators have a gradient smaller than this threshold, you stop there. Now the gradient doesn't necessarily guarantee, that it doesn't tell you how much you're missing.
Yeah.
And I think our selection criterion kind of tries to do that and does it maybe a little bit better by trying to evaluate how much we're discarding. So yeah. So you can see, in fact, that in our technique that roughly the energy error remains, I would say, constant up to some level. Yeah, but we don't have, we don't see these kind of drops. Thanks. That's a good question.
Thank you.
Thank you. I really appreciate both parts of it. And I would have a question concerning the first part, the projective approach. Actually, I'm interested in the importance of maybe an extended or more.
Let me recall. I think we always use canonical Archer-Fock orbitals, which are probably, I would say, not optimal. No, okay. So for example, one extension that would be interesting is something like you did, where you combine orbital optimization with the selection of the ansatz. And I see that maybe as a better way to proceed. Well, I would say is immediate improvement upon what we did would be MP2 natural orbitals, but we haven't tried that. We played a lot with the orbitals when we looked at the downfolding, and there we have, we know better how the downfolding works with different types of orbitals, and it's very important to pick the right orbitals to make sure that the quantum calculation comes out to be accurate.
Well, then, as a follow-up question, what kind of orbital in the second part of your talk?
So CF orbitals in the second part help a lot. So if you try to do the downfolding with Hartree-Fock orbitals, you don't get very good results. I mean, you get decent results, but they're not as good. What was interesting to us is for the second part, and I don't have the data here, we use couple cluster natural orbitals, and these surprisingly work very well. So that's a kind of a way to avoid so in the scheme that I presented, you have to do potentially two quantum calculations. One to get a reference state, and one to get finally diagonalize the effect on Tony. Sorry. But here we found out if we do a couple cluster calculation here, get the density matrix and feed it to this DSRG, we can get decent results. Yeah. So that's maybe a way to go.
Okay, and maybe we can have a discussion.
Let's discuss at the coffee time.
Yeah, we'll have a discussion.
So by apology, can you comment on folding, because I'm not an expert, but I just wanted to understand. Is this, can you make it or is it subjective? Not.
So this unfolding is not strictly variational. And it all has to do with many technical details that I didn't discuss. So here you're doing a unitary transformation, and unlike non-unitary transformations, we cannot do those. These don't have closed form. No. So if I expand this in a commutator series, this series doesn't truncate. So what we have to do is we have to find a way to deal with that issue. And as we deal with that issue, for example, the technique that we use is we keep adding these commutator terms, but we limit their body character. So we stop the 2-body. And if we have 3-body elements, we throw them away. So that's an approximation that has been studied and it's well understood. But it's an approximation. So, and as a consequence, we lose variationality. So the caveat of using this technique can be used only to describe weak correlation effects. So it's like couple cluster theory. You won't use it for strong correlation.
I've got several questions, but maybe we can discuss that later. But about the first part of your talk, is it related to some kind of Davidson technique? It's instead of using the Hamiltonian, you are using this transform Hamiltonian with a U dagger HU, because it's very related to that, to calculate the residual and to transform the residual to with some kind of energy difference things to improve your convergence of your kind of grid of space.
Yeah,
For me, it's very similar to what.
I agree. Yeah. But in Davidson, you don't transform the Hamiltonian. Well,
yeah, but you
so
you transform the. You are in a basis,
yes.
but you transform. You calculate your residual, and then you transform your residual to improve the convergence of your iteration.
Yes.
So with respect to Lanczos, you reduce the number of iteration because of this transformation. I think for me it looks similar, except that you're using not the Hamiltonian as operators.
Yes, but when I do the technique, I have a vector. I have a vector, and I'm rotating that vector until I reach the residual equals 0 condition. In Davidson, you have a linear combination of vectors that you optimize. So that's where I see the two techniques depart. In Davidson, you have multiple vectors that you combine together. Here, I'm always rotating a vector, and I'm using the residual to guide me in which direction that vector is rotating.
So you mean you get only one vectors?
Yeah.
So it means that you are. Yeah. It's equivalent to restart your Davidson each iteration.
Yes.
Somehow.
Yes.
Okay.
Yes, like that.
Okay.
Because it's very impractical to do the linear combination of the states on the quantum computer. Yeah, that's a good point. That's an interesting perspective.
So the last comment about the using have been used in quantum chemistry, BCCD, and they use that that improves the stability of some kind of copper cluster.
Yeah, no, and that's definitely not something that I have to point out. We discovered, like, there's this work of Shero that I've seen, for example, in the early 2000s that used couple cluster as a starting point, CASA-CF, or as a replacement. You mentioned Bruckner.
Yeah.
Yes. No, that's definitely not an aspect we found that we discovered, but we found that those density matrices and orbitals are good enough to skip the initial CASA-CF calculation, even in this context.
Yeah, but it was on H2, so H2, the R3 orbital are good. They're almost as good as the one of CAS. Because of the symmetry. Because of the symmetry.
Yeah. Well, for H2 we tried a lot of things. We tried R2-Fock. We used unrestricted R2-Fock, natural orbitals, and these always have this issue of the symmetry breaking, and you see that. No, you.
Okay. So
because you first are restricted and you unrestrict, and there you get discontinuity.
So because you unrestrict, but if you're using restricted R3-Fock all the way, the orbital will be fully symmetric.
Yes, but I think in a bigger basis, you see more an effect
Yeah,
where
probably.
they're not as good. And the
Yeah,
small
yeah.
basis set, they're good.
If I can allow myself to ask a last question, I would need to come back to David.
Yes.
Somehow with the QPE, you will have a number of measurements that is basically the size of the matrix. I mean, the residual to measure. You have all the residual to measure, so all the elements of a column. And it's work because the matrix is sparse. So I guess you can reduce drastically the number of measurement by optimization. The matrix is sparse. Is that the reason?
Yes, so if you select the operators that you put in the ansatz, then you have a reduced number of quantities that you have to measure. But yes, and
will it work if it's not a sparse matrix? Can you select efficiently the pertinent operator if you have not a sparse matrix? Or is his work is the density of a matrix? How you need only a few states or a finite number of operator to
sorry,
consider.
What matters is not the sparsity of the matrix. At least for the ground state, what matters is this kind of first column. So here I add like this figure here. So we don't really care too much about this. We just care
but
about this column here.
so
So yeah, so if that column is sparse, then like its selection technique will be very helpful. If it's not sparse, then I think we're in trouble. But I want to, I mean, to put things into context is like typically VQE is actually even optimized just using energy, which is it's extremely expensive. Moving to a residual based or gradient based technique like in VQE, I think it's much better because now you have some information, clear information where you need to go to get a better answer. But yeah, it's still expensive. Like, yeah, if we did an ansatz with singles and doubles, we would have to compute like into the fourth of these elements.
Somehow the energy landscape that is behind is much more simpler because you have much more tree on the energy landscape as looking at the residual. But I mean, because it's quantum chemistry Hamiltonian are sparse, so it's fine. It's pretty cool.
Yeah.
Thank you. I think it's time to take a coffee and we'll come back in 10 minutes. And thank you so much again, So at 11:05, we are back.